Okay, so where we left off was that EK max was equal to HF minus WO. And EK max was the kinetic energy of the electrons that were being released from the photosensitive surface. You will see them referred to in questions as photoelectrons, and that simply means it's the electrons released as a result of the light from hitting the photosensitive surface. The HF is the energy of the photon. We also call this EP, energy of the photon. So Planck's constant times the frequency of the photon, it's the energy coming in to strike the surface, trying to release the electrons. And then the minus WO, and where the last video ended, it was that WO was the energy that the metal needs to release the electron. So the metal won't just give up its electrons for nothing. It has a certain minimum energy that the light needs to have before it'll release the electron. Okay, so WO, the energy the metal needs to release the electron, and it's referred to as the work function. Okay, and we know that it's just an energy, and it's actually, okay, wait, maybe before I do that, let me do an example and I'll come back to that. So think about a kid shooting a basketball. The energy that the kid puts into the basketball is like the HF. If the kid doesn't put enough energy into the basketball, it doesn't make it to the rim. And if it doesn't make it to the rim, it's not able to go through the net. So it needs to at least have enough energy to get it up to the rim. And if it does, then it just gets to the rim and it falls through. If the kid is able to give it more energy than that, then the HF is going to be bigger than the WO, and there's going to be energy left over. And that's the EK max. Now, I was using that example because it was the one that, remember in the fall, the woman that won the Nobel Prize in Physics was speaking at UNB? And she used that example. And I'm trying to think of how she made it all work. So let me go back to my own because I don't quite remember. I usually say, okay, imagine that you're stuck in your house. Hard to imagine, eh? And you can't go out, and your parents won't let you. But you have this really nice aunt who wants you to have a little freedom. So the aunt says to your parents, how much money do I need to send you for you to let your kid to go out? So your parents set a minimum limit. They say, okay, well, you need to send us $20. $20 and we'll release this child. So your aunt sends the $20. So the HF, the packet of money for the electron, the packet of energy that comes in is $20. And that's exactly what your parents require. And so if your aunt only sends the $20, then there's nothing left over. So you can go out of your house, but you stand on your doorstep because you don't have any money to do anything. There's no energy left over. When the light coming in just matches the minimum energy that the surface requires, there's nothing left over. And when that occurs, this side would be 0. Take the HF over and you'd see that WO equals HF. And that F is the threshold frequency. And so the equation that I stopped myself from writing down here is that we know WO is equal to HFO. So if we know the threshold frequency, then we can find the work function. Okay? But let's suppose your aunt realizes that if she only sends $20, you're not going to have any money to go anywhere. So instead your aunt sends $30. Okay? So an envelope comes, there's $30 in it. Your parents take their 20. So the HF is 30. Your parents take their 20 and there's 10 left over. And that becomes the traveling energy that you have, the traveling money that you have so that you can go to Fatty's and get pizza or something. So however much is left from the packet of energy that's coming in to strike the metal, once the metal takes away its required energy, whatever's left over, that's what the electron gets to travel across the evacuated tube. Okay? And that's why as you increase the F, the frequency of the light, this goes up. The WO doesn't change. It's constant for a given metal. Aluminum has one WO, sodium another, copper another. So as long as you're using the same metal, the WO stays the same. So if you increase the frequency, then the traveling energy of the electrons gets bigger. The kinetic energy gets bigger. And that's why we have this line, these lines. Okay? So as the F goes up, the kinetic energy goes up. But it's also why we have these graphs, right? Because in increasing the intensity of the light, all that is doing is it's not changing the amount of HF, it's just changing the number of packets that come in. And each packet is able to free an electron. It's kind of like your parents realize you have 3 other siblings, your aunt realizes you have 3 other siblings, so they send 4 envelopes of money, 1 for each kid. Okay, so the number of packets just increases the number of electrons being released, but it doesn't change the amount of energy in each packet. So that goes back then to these questions. As you increase the intensity, it doesn't change, the intensity is the number of packets. It doesn't change the amount of kinetic energy that each electron that's released has. Instead, I don't know where the other sheet is. Instead, it changes the number of electrons being released. There it is. I was trying to figure out what I did with the other math. Okay, so when you change the number of electrons, it doesn't affect the values in this equation at all. It just affects the number, as the number of photons going in, it just changes the number of electrons being released. But changing the frequency doesn't change the number of electrons, it changes the energy each electron has. Okay? Another way we can find this WO is using that stopping potential that we had originally, or second time around, right? Remember in this diagram, we said, okay, we're going to increase the voltage of this stopping potential, of this power supply, and as we increase the voltage, then these electrons that are freed experience more resistance, right? A bigger repelling force as they try to make it to this electrode. Okay, and so eventually, if we make it big enough, we can stop all the electrons coming across. And so that's called the stopping potential. Okay, and it's VO. All right, maybe one more thing, and that is the measurement of the energy. A joule is what we usually measure energy in. But a joule is a huge amount of energy when we're talking about electrons. It's really, 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 really big. And so instead, we often use a smaller unit that is called an electron volt. And its abbreviation is a small e for electron and a capital V for volt. It's a much more reasonable unit. It's kind of like using a kilometer to measure the width of a hair when we use joules for the energy that an electron is needing here to be freed. Okay, so an electron volt is a much better unit. And 1 electron volt is the energy of 1 electron when it's accelerated across a potential difference of 1 volt. So imagine we have 2 plates and the potential difference, the delta V, is 1 volt. And we're going to move 1 electron across it. Okay? So the 1 electron volt is the energy that this 1 electron picks up as a result of the work we've done in moving it across a potential difference of 1 volt. So it takes us back to that equation V equals W over Q again. Okay? And remember, W is the energy, work done, change in energy. So 1 electron volt, or 1 joule, if we do 1 joule of work to 1 electron, moving it across 1 volt. Okay? Well, what